Hi, good evening, and welcome to lecture number 17 for MT225. Let's see here. Tonight we're going to continue on method of sections. So we'll do a couple more example problems, have a couple more for you to work out. We have homework 6, which is our method of joints homework due today, and I'll open up the floor for questions on that one here in a moment. We will be having quiz 5 on Monday. Now, quiz 5 is on the content for homework 6. So at some point over the weekend, I'll grade homework 6 and I'll post the solutions. And you can check out what you did, hopefully fix any misunderstandings you've got, and then we'll take a little quiz on it on Monday. So I'll post that probably sometime in the afternoon on Sunday. I'll post the quiz, and that'll be due midnight Monday, as we've been doing. And then homework 7, which is our method of sections homework assignment, that has been posted, and that is due in 1 week. That'll be April 7th. So let's see, homework questions. The question's been asked already about homework number or problem number 3. So we'll take a look at that one here. So let's go over to the homework assignment, homework number 6. All right, there's homework number 6. So problem number 3 is this one right here. Let me zoom in on it a bit, and we'll there's view. We'll go with text width on that. There we go. All right, so there's our problem. We've got a reasonably complex truss. There are a lot of members to this one. And let's see, we've got 1, 2, 3, 4 members going across, and then we've got 5th, 6th, and 7th on the bottom there. So that's a lot of members to work with. When you're working method of joints, which is all we have for this problem, you have to make sure you're using joints that only have 2 unknown members. So that's going to mean the only places we can work right away would be A and C. And then with A and C, we could jump to B and then maybe over to E or D. Either one of those would work. So let's go ahead and set it up here. The goal of the problem, find the states, so the forces of all in all truss members, and determine the state of tension and compression of each. And we're looking for 3 sig figs in our final answer. So let's go ahead and run this down. I'll go ahead and copy it over first here. So we've got our horizontal chord. Now this thing is somewhat reminiscent of sort of a bridge structure. This is kind of like a railroad bridge or something like that you might see driving around. Let's see, we got a big cross member there. There we go. And let's see, we've got a pin to support at A, roller at C. At D, we have an externally applied force of 50 kilonewtons. We've got at E an 80 kilonewton applied force. Then we've got some geometry. The whole thing is 3 meters tall, about 10 feet tall or so. And then across the bottom, we've got 2 meters between A and B, 5 meters between B and directly below D, and 1 meter to the roller. Looks like 8 meters across. All right, so let's go ahead and work out this problem. So to work out this problem, first thing we have to do is solve the external problem. So we have to figure out what the reactions are at A and C. Otherwise, we have too many unknowns to work any of the joints. We'd have 3 unknowns here at A, we'd have 3 unknowns at C, and we'd be in trouble. So first thing to do is we'd draw the free body diagram of the whole structure. And when we're drawing the free body diagram of the whole structure, we don't have to care about any of the internal details. So it's easier to draw the free body diagram. So here's our system boundary. System boundary will go around the truss this way. So for our external problem, that'll be our system boundary. So drawing to the right of that will draw the shape of the truss. Looks something like that. And we can ignore all the internal structure for now. We have still our externally applied forces. We have that 80 kilonewtons over here and 50 kilonewtons there. At C we've got a roller, and the roller exerts a force perpendicular to the surface it's on, so that would be RCY in that case, the reaction at C in the Y direction. At A, we've got a pinned support, so we'd have RAX and RAY. And we'll borrow the geometry from the drawing on the left. So let's go ahead and do our sum of forces in the X and Y direction and sum of moments about a point. So sum of forces in the X direction, all we've got is RAX. So that's 0. No side loads on this, so nothing for the pin support to react against. All we've got are vertical loads. So in the Y direction, we've got the same thing that every Y equation says. The sum of the forces up have to oppose the forces down. So we have RAY plus RCY minus 80 and 50, 80 and 50 total. That's 130. So that equals 0. And then we need our moments. And we'll pick our pivot point at A. That'll knock out RAX and RAY, but all the other forces are going to have moments. And we'll figure out the arms from the drawing with the measurements on it. So sum of moments about A. We have RCY. RCY is 8 meters away, so we've got 8 RCY. And according to our coordinate system, counterclockwise moments are positive. If we pin at A and push up at C, we definitely have a counterclockwise moment, so positive there. The 80 kilonewton force, according to this drawing, the line of action of 80 newtons is 2 meters away from A. So we have 2 times 80, 2 meters times 80 kilonewtons. So that'd be 160 kilonewton meters. And if we pin at A and push down up here, that would be a clockwise moment, and clockwise moments are negative. Then we have the other external force here, this 50 kilonewton force. Well, the line of action of that 50 kilonewton force is 7 meters from A. So we have 7 times 50, that'd be 350. If we pin at A and push down over here at D, that'd be a clockwise moment, and clockwise moments are negative. And those are all the moments we've got. So those are our equations of equilibrium for the truss. To solve, we can work with the moment equation first. Usually the moment equation is the first place we go. So we've got 160 and 350. That added together is 510. If we add it to both sides, we'll end up with 8 RCY equals a positive 510. And divide both sides by 8. And we get RCY is 63.75. And the units, it's a force, so it's kilonewtons in this problem. Now that we know RCY, we can go into the Y direction equation and replace RCY with 63.75. And if we go and figure that out, we've got 63.75, we got minus 130. That means RAY has got to be 66.25. So RAY is 66.25 kilonewtons, since 66.25 and 63.75 will add up to 130. So there we've got our reactions. And that's the first step to being able to solve the method of joints problem. So schematically, let's go back to our original picture here, and we'll draw those in. We've got right here at A, we've got a force of 66.25 kilonewtons, and over at C, we've got 63.75. So pushing up right there at the roller, 63.75 kilonewtons. Let's just do a quick check and make sure that that the distribution makes sense. We've got 50 kilonewtons here, so most of that 50 kilonewtons, since it's only 1 meter away, most of that's sitting on C. We've got this 80 kilonewtons that's farther away, but some of that's going to contribute, so it's going to share some of the load, which is why we see roughly equal loads here, but slightly lower load on C than we do on A. That heavier load of 80 kilonewtons is closer to A, so it loads that down more. And the distances are a little misleading in the schematic. They're not exactly to scale. This is only twice the distance of this, so it's not like it's very far off of being directly above. So we've got our reactions. Now we can go into the actual method of joints. So for method of joints, we've got to pick a joint that is that only has 2 unknown members associated with it, and work out the equilibrium. And to help us with that, or at least to give us someplace to put our information, let's draw up a table. So we'll draw up our table of loads and states of tension and compression. So we'll have tension and compression. We'll have our load in kilonewtons, and we'll have our members here. I think I had 7 members in there total, so we'll give a row to each member. There we go. And then, excuse me, labeling these out just in alphabetical order, starting today. We've got AB. We've got AE. We've got BC. We've got BD. We've got BE. At C, we've got CD. We've already got BC, so we don't need to deal with that one. And then at D, we've got DE. So there we go. We've got all 7 members there. So let's go ahead and work out the equilibrium. Joint A or joint C would be the place to start. They're the only places where we have only 2 unknowns. And in order to work out the equilibrium there, we're going to need angles. We need the angle here, the angle here, and then when we draw our free body diagram, we'll be able to figure out what those angles, where to draw those angles correctly. Well, the angle at A is a little easier to get. We've got a right triangle here, 2 meters wide and 3 meters tall. So we can use the inverse tangent of 3/2 to get that angle. And the inverse tangent of 3/2, I'm getting 56.310 degrees, and I'll keep 5 sig figs since I want to make sure I'm going to get 3 good sig figs in the end. So here we have 56.310 degrees. Over here at C, you got to be careful. That angle is inside this really tall, skinny triangle. That's 1 meter on the base and 3 meters up. So you got 3 meters over 1 meter. That's the inverse tangent of 3/1. And the inverse tangent of 3/1 is 71.565 degrees. And we'll get the angles elsewhere as we need them. So let's work out A and C. That'll get us 4 out of the 7 members, more than halfway through the problem. So let's start at A first. So let's draw our free body diagram for A. If you're having trouble figuring out how to draw the free body diagram, draw a little circle around that joint and make sure you represent everything that crosses or touches that circle. Well, that circle interacts with 3 forces. We've got our vertical force of 66.25 kilonewtons. We've got whatever force member AB exerts, and we've got whatever force member AE exerts. So draw what you know first. So there's joint A. We've got an upward force of 66.25 kilonewtons. Now, I don't exactly know which way to draw AB, but if you think about it a little bit, you can kind of come up with a convincing argument for the direction for AE, because we've got to have something that has an up or a down force here. We've got an up force, so we need something with a down force to oppose it. Member AB is horizontal, so it can't apply an up or a down force. So the only thing that's going to be able to apply a down force would be member AE. So it makes most sense to draw member AE's force down here like this. So this would be the force due to member AE. And then knowing that, we have a better guess for what direction AB needs to go in. Because if AB pushes to the left, we've got no force to the right to oppose it. So we end up with something that can't be equilibrium. On the other hand, since FAE already pulls a little bit to the left, it makes sense to draw member AB pulling to the right. That way we have a chance at equilibrium. Remember, we want our free body diagram to look like it's a tug of war that no one can win. Now, it's possible that you might have to just do a guess at some point. You might not have enough information to really say, well, it goes this way or it goes that way. So you got a 50-50 shot. Guess one and then draw the other so that it makes sense and it looks like equilibrium. If you either both your answers will come out positive or they'll both come out negative. So you'll be able to come up with a solution there. Now we need to make sure of the angle we're using here, and to see that, which angle and how to draw it, extend the line for AE and for AB and look for something similar over here. We're looking at this angle right here, 56.310. This angle here would be the same. So the angle of AE from horizontal is going to be right here. So that's the angle, 56.310 degrees. You want to make sure you don't put that in the wrong spot and accidentally label it as a complement. And you generally will have consistency with it. If the angle up top here is measured to horizontal, then the one underneath will be measured to horizontal too. Don't change it from measuring to horizontal to measuring to vertical. That'll guarantee you'll flip your sine and cosine and you won't get the right answer. So let's draw our coordinate system, positive x and positive y. And now we can go ahead with our sums. So we'll push that off to the side for a second here. Sum of forces in the x direction. We've got all of FAB and it's to the right, so it's positive. We've got a piece of FAE to the left. So we can write that as minus FAE, but we have to figure out what that piece is. It's the adjacent piece. X here would be the adjacent side to the angle of 56.310, and adjacent goes with cosine. So we have the cosine of 56.310 degrees, and nothing else in the x direction. So that sum is 0. In the y direction, we have a positive 66.25 kilonewtons. And we have a negative piece of FAE. Since we already used cosine up here, we're really looking for the adjacent side to that, or to the opposite side of that angle, this vertical piece, and that goes with sine. So we have minus FAE sine of 56.310 degrees. So that equals 0. So there we've got our equations of equilibrium. The first one we can't solve. We've got too many unknowns there. But the second one we can. If we add this whole term, FAE sine of 56.310 to both sides, we'll have 66.25, and I don't know why I drew the kilonewtons in there, but 66.25 equals FAE sine 56.310 degrees. Divide both sides by that sine. And that'll give us our value for FAE. So FAE, 66.25 divided by the sine of 56.310. We end up with 79.623. So 79.623, and that's kilonewtons. Came out positive. So we know we've got the correct direction. Let's go ahead and find our member AB, and then we'll go and figure out whether we've got tension or compression. So member AB, we can figure out by substituting in for FAE 79.623. So 79.623 times the cosine of 56.310. That's 44.167. So we have FAB minus 44.167. And that equals 0. So FAB equals 44.167 kilonewtons. Also came out positive. So we know our directions are correct. So we've got our values for how much load is carried by member AE and member AB. To figure out whether we're in tension or compression, remember the basic picture for method of joints. For method of joints, if we have a member that is in tension, so member in tension, put that off to the side here. A member in tension pulls its joints inward. So a member in tension will take the supports that it's on and try to bring them closer together. But a member in compression tries to expand out, so it pushes the joints apart. So with that key, we should be able to figure things out as long as we know where the members are compared to the forces on the joint. Well, let's look at member AB. If we compare, I've got those right next to each other, so we can compare those pretty easily. We've got the force due to member AB is to the right. There's joint A. Member AB is physically to the right of joint A. So member A, B is over here. So that looks a lot like this end of this picture. Joint A is being pulled toward joint B because member AB is in tension. So we can go over here to our table, and I'm not going to round into the table here. We'll draw a different table for our final answers, because we're going to have to refer back to several of these, and I don't want to be searching through the paperwork trying to find where that was. So we'll write out our 5 sig fig values here. Member AB carries a load of 44.167 kilonewtons, and we've determined it's in tension. Now member AE, comparing the physical drawing to the free body diagram, member AE is up here. Member AE is to the upper right of joint A. So member AE is pushing joint A away. Only members in compression can push something away. So member AE is in compression, and it carries a load of 79.623 0.623 kilonewtons. So that's about all we can get from joint A. We've solved everything there is to know. So we have to go to a different joint. Now we might look at joint B here, but although we know member AB, we're missing member BE, we're missing member BD, and we're missing member BC. There are 3 unknowns at joint B. There are also, we could go up to joint E. Joint E would definitely work next because we've got member AE. We'd only have 2 unknowns there. C also works because we've only got 2 unknowns there. We don't know anything about BC or CD. And so C we could jump to next. If you went to E instead, that's okay too. You'll get to the same place in the end. So let's go ahead and work out joint C. So again, start with what you know. Here we've got joint C. We have a 63.75 kilonewton upward force on it. So 63.75 kilonewtons. Now again, same argument as A, we need something to be pushing down to oppose that up if we've got any hope of being in equilibrium. So member DC, a good guess to the direction member DC goes in, be down here. And with that being in place, makes sense to draw FBC over here. And just like with A, we've got our angle here to horizontal. That's going to be this angle right there, 71.565 degrees. So there's our free body diagram for joint C. So let's go ahead and work out our sums there. It should be substantially the same as working with joint A, same basic equations. So the sum of forces in the x direction, we've got all of FBC, but that's to the left. And we've got a piece of FDC. It's the horizontal piece, the adjacent side. So we have FDC cosine 71.565 degrees. And that equals 0. We can do our sum of forces in the y direction, where we've got 63.75 up, and we've got the sine piece of FDC down. That's sine 71.565 degrees. So there we've got our equations of equilibrium. We can solve y pretty quickly. 63.75 equals FDC sine 71.565 degrees. Divide out the sine, and I'll save the algebra space on the paper and just jump to the calculator. 63.75 divided by the sine of 71.565. We get that FDC is equal to 67.198 kilonewtons. So remember DC, did I say DC? CD should be the correct. I knew that sounded weird. Say CD. Just in sticking with our alphabetical order standard here. So FCD, 67.198 kilonewtons. Positive, so we know we've got the right direction. We can go up to our x direction equation and plug in that 67.198 kilonewtons. And if we take 67.198 times the cosine of 71.565, we get 21.250 plus the negative FBC equals 0. Make sure you don't get tripped up in your negatives. If you add FBC to both sides, you'll get FBC equals 21.250 kilonewtons. So it also came out positive. So we know we got the direction right. So let's run those numbers over here into our table. Member BC carries a load of 21.250 kilonewtons. And member CD carries a load of 67.198 kilonewtons. We still have to figure out tension and compression though. So let's draw in the members. Member B, or joint C, we have member BC to the left of joint C. So member BC is pulling on the joint. It's trying to bring joints B and C together. That's tension. So member BC is in tension. So we can check the tension box there. Member CD, if we go and draw member CD in relative to joint C, member CD is up and to the left. So it's over here. And that's pushing joint C away. Only members in compression can push the joints apart. So member CD is in compression. And that fits with some of the intuition I talked about last time. Usually with gravitationally loaded structures, we've got weights sitting on a structure. Generally, the bottom of the structure is in tension and the top and the sides are in compression. So we got member AE and member CD, both of those are in compression. And member AB and member BC, both are in tension. That fits with essentially bending. So we've only got 3 members left to figure out. And I think we can, let's see. We can do either B or E next. D could work too, but I'd stay away from D because there are going to be 2 different angles involved. There's going to be this angle for CD and this angle for BD. So I would leave B. I would only do D as a last resort. At joint E, I've only got 1 angled member. Everything else is at right angles. So that makes life easier. At B, I've got the same situation. I've only got 1 member at an angle. All the rest are at 90 degrees or horizontal or vertical. So by looking ahead a little bit, you can save yourself some time and effort and save yourself a lot of sines and cosines, especially of different angles. So well, let's go to joint B next. Joint B will work fine. We need to figure out an angle for that though. We need this angle right here. Fortunately, we can get that pretty easily. We've got a 5-meter base and a 3-meter height if we draw that right triangle right here. So 3/5 inverse tangent, that's 30.964 degrees. So we've got the angle. Let's go ahead and work out B. We'll save E for last. So draw the free body diagram at B. Now here, we're going to have to use information we've already solved. We know members AB and BC. And the thing you have to be most careful about is drawing them in the right direction. So again, you might have to refer to your picture of tension and compression and refer to where the member is to figure out what direction it's going in. That way you can get the right directions of things that you know and make reasonable decisions about the directions of things that you don't know. So let's take a look here at AB. AB is physically off to the left. Now remember, AB, according to our table, is in tension, and tension pulls the joints together. So while joint A was pulled to the right, joint B is pulled to the left. In order to bring these 2 together, joint A has to go to the right, joint B has to go to the left. So the proper direction to draw member AB's force in is to the left, and we know how much force we've got. We've got 44.167 kilonewtons. Now, member BC, it might be safe to assume it's the opposite direction because it only makes sense that way, but you should come from a point of view of understanding it from this tension. So we know member BC is also in tension, so it's going to pull joints B and C together, which means joint B is pulled to the right. So joint B is pulled to the right by member BC. That's 21.250. Now we've got our unknowns. Now we've got member BD and we've got member BE. Unfortunately, there's not a good way to kind of figure out, at least easily, not without playing with the numbers and all that, to figure out whether BD is pushing or pulling, or whether BE is pushing or pulling. As we've got all sorts of other forces at play, there's sufficient complexity here where it's a toss-up without a lot of careful examination as to whether BD pulls or pushes or whether BE pulls or pushes. So we have to make a guess. And I'm going to make the guess that member BE is going to push down. That's completely a guess. I'm just 50-50 in it here. I'm going to assume member BE pushes down. So that's the force due to member BE. Then the only reasonable assumption for me to make is that BD pulls up and to the right. And then we've got that angle right there of 30.964 degrees. Now, I could be wrong. And if I am wrong, then I'll get negative answers for both of these. And that'll mean I'll have to just be careful about how I interpret tension or compression. I'd either redraw it the right way after I've done all the math and then interpret tension or compression, or figure out tension and compression from what I've drawn and then just flip them, check the other box. Either way works. So let's see how it worked out. Take our sum of forces in the x direction. In the x direction, we've got all of this 21.250 degrees. We've got all of this, and that's to the right. I don't know why I wrote degrees there, but 21.250 to the right. We've got 44.167 to the left, so minus 44.167. Nothing from FBE. And then we've got a piece of FBD. It's to the right, so it's positive. And it's the adjacent side, so it is cosine. Cosine of 30.964 degrees. So that's our x direction sum, so that'll be equal to 0. Then our sum in the y direction. We've got all of FBE down, and then we've got a piece of FBD up. So we have FBD, it'll be sine of 30.964 degrees, or 30.964 degrees. And that'll equal 0. So this time we can't work the y direction equation right away. We have the x direction that we have to use. So let's see how that comes out. If we combine those two numbers together, we've got 21.250 minus 44.167. That gives us a negative 22.917 plus FBD cosine of 30.964 equals 0. If we add 22.917 to both sides, we've got FBD cosine equals 22.917. And if we divide both sides by the cosine of 30.964, we get 26.726. So FBD is 26.726. All right, so it came out positive. So I guess I guessed correctly. Member BD really does pull joint A or joint B up and to the right. So we can fill that in the table. We've got member BD carrying 26.726 kilonewtons. To interpret tension or compression from that, well, member BD is up there like that. Member BD is up and to the right compared to joint B. So according to our drawing for tension or compression, that's tension. Tension pulls the joints inward. So we can check the tension box on that one. Going back to the equations, now that we know member BD, we can go ahead and solve for member BE. So if we plug in the 26.726 kilonewtons that we had for BD, we've got negative FBE plus 26.726 sine of 30.964 degrees equals 0. If we add FBE to both sides, we'll just get FBE equals the value of 26.726 times the sine of 30.964. So that's 13.751 kilonewtons. So that came out positive. So we know it's got the right direction in our free body diagram, and member BE is above joint B. So member BE is up here. So we've got member BE like that. Pushing joint B away, that's compression. So member BE carries 13.751 kilonewtons in compression. So we're almost there. One more member to work with. This is why there were only 3 problems on the homework assignment, because these do take a bit of time to work through. Let's go ahead and do joint E. It's the last one we've got. And remember, on the last joint, you only need one of the 2 equations. So we'll see which of the 2 equations work out to be easiest, and we'll solve that. We'll have unknown. We have everything else known. We just have to be careful about drawing that free body diagram. So joint E right there. Start with what we absolutely know is this 80 kilonewton force downward. So we'll put the 80 kilonewton force in. Now we'll start with the with what we know from the table. We know member AE. Now member AE is, according to our chart, in compression. And in compression, the joints are pushed outward. So joint E is going to feel a force like that. And it's going to feel a force of 79.623 kilonewtons. And we'll also have an angle here. Now that angle is the same as the angle down here, 56.310 degrees. Then we've got member BE. Member BE also carries a force in tension, in compression. So it's also pushing away. So joint E is being pushed up by member BE. So there's an upward force here of 13.751 kilonewtons. And again, if you're not sure, make sure you draw that little circle and count up your forces. You've got 1, 2, 3, 4 forces. I've only got 3 in my free body diagram, so I must have missed one. And it's member DE. Member DE exerts a force either to the right or to the left. The only one that makes sense from what we've already drawn is to the left. It's the only way we're going to get a 4-way tug of war that no one is winning. So that's member DE. And with a little bit of thought, you can kind of guess which way you should go as far as the sum of forces. If you look at building up your equations, you got a lot more components in the y direction than you do in the x. And in fact, the y direction equation won't even get us anything in this one. I don't think we've seen this before, but notice how our unknown here is only in the x direction. Before, we've had everything else and our unknown on an angle. This time, we've got no choice. We can only do the x direction equation because all the y direction equation is going to tell us is 0 equals 0. So when we take the cosine or we take the sine of 79.623 and add it to 13.751, it's going to be 80 kilonewtons. So we got to go with the x direction equation. So let's take our sum of forces in the x direction. We've got all of FDE to the left. And then we've got the adjacent piece of 79.623. So we have 79.623. Adjacent goes with cosine. So cosine of 56.310 degrees. That equals 0. So let's find out the value. 79.623 times the cosine of 56.310. That's 44.167. So we have negative FDE plus 44.167 equals 0. And if you add FDE to both sides, you'll get FDE equals 44.167 kilonewtons. So we get 44.167 kilonewtons. So we can go over to our table and fill that in. And to interpret tension or compression, member DE is to the right of joint E. So member DE is over here. That means that member DE is pushing joint E away, and only members in compression can do that. So we can check the compression box there. So there we go. We've got our table filled up. We've got our states of tension and compression. Again, we're looking at essentially bending in the structure. So DE we expected to be in compression, and AB and BC we'd expect to be in tension. Whether BD is in tension or compression generally will depend on what these forces are. That's what kind of makes it a little hard to guess what direction things will go into, because depending on some loadings, it might be tension, some it might be compression. So to finish up the problem, we can go ahead and draw either a force summary diagram or draw our table just with proper rounding. And the force summary diagrams get a little cluttered, so we'll go ahead and draw the table. And a table is what I'd have you fill out on the exam anyway. So there we go. AB, AE, BC, BD, B, C, D, and D. Make sure you copy things over correctly, especially with tension or compression. It's one of the things I look at when you build up a table like this, especially if I give you a table to fill it out, like I would on an exam or in a quiz likely, is I'm looking for that pattern to see that the tension and compression checks are in the right places. And what did I do there? And that pattern, oh, I doubled up there, didn't I? Careful on that. There we go. So now let's round our loads off. And the specification for this problem was 3 significant figures. So we can go ahead and round those out. 44.167, that'd be 44.2 kilonewtons. 79.623, 79.6. 21.250 would be 21.3. 26.726 would be 26.7. 13.751 would be 13.8, 67.198, 67.2, and 44.2. So there we go. There's our final table. And the problem's done. If you really wanted to be sure that you were right, you could go to joint D and plug in everything that you know and see if it comes out to be zero, sum of forces in the X and the Y direction. That'd be a good validation of your results. Not required, just like checking an equation. It's not required, but it's not a bad practice to use. All right, so there's the, that's problem number 3 on the homework. Any questions there?
Nope.
All right. So let's go ahead and switch back to the notes. So there we go with our homework questions. I usually expect that the homework questions on method of joints and method of sections, they take a little while to work out. So we're right about where I figured we'd be for that. So our only goal today is a little bit more method of sections practice. So we've got a new homework assignment out for method of sections. I'll do another example of method of sections, and then we'll give you a couple to work on. So not much really to say other than just doing the exercises. And because I usually forget to come back to the notes and say next time on Monday, we're going to get into another type of structure, what we call a frame. So let's look at a truss problem. So let's do one here that's a little bit different, well, than what we've seen so far. We had a lot of rectangular stuff in the trusses that we dealt with so far. So let's try something that looks a little bit more, interesting. So a little more practical too. So here we'll do a roof truss. So a roof truss is going to look something like this, at least on the outside chords. And let's see, I think we'll do a couple of verticals there. And then we can do one right there. And we'll do something like that. So that's a typical roof truss. And I forget which one it is. I don't remember my truss names, but all these trusses that you see out there, they have particular names. I don't remember if this is a Pratt truss or a Howe truss, or it's probably one of those two, but there's a whole table of them that you can go and find. But this is a typical roof truss, usually for a pretty good size span. In fact, we're going to make the span on this one, let's say, we'll go with 24 feet. It'd be a typical application for it. So we'll put a pinned support here and a roller support here. We'll do 4 bays at 6 feet, and at 6 feet each, that'll be 24 feet. So a typical 24-foot span. And we'll make it let's make that 8 feet tall. And we'll put some load on this here. So let's put 10 kips up at the top. And over here, we'll have somebody hanging 4 kip load. So maybe they've got a couple tons they want to jack up onto this thing or hoist up onto this, and they've tied right to there. And what we want to find out is what are going to be the stresses, or what are going to be the forces carried by those 3 members. In fact, let's go one step further, since this is a reasonably complex problem. We want these 4 members here. So let's figure out what we can do here. So first thing we have to do is figure out the reactions at the supports. Now, if it was just that 10 kips pushing down, we could split it evenly and we'd be done. But we've got something throwing that balance off. So we've got to deal with the whole free body diagram. So let's go and find the reactions at the supports first, and then we'll do method of sections. So let's see, we'll keep that on the screen. So here we've got our external problem. Right around here, we've got 4 kips down. We've got support force there and here, and I can label these A, B, C, D, E, F, G, and H. So there we've got our members labeled. We've got a 10 kip force right at the top. We'll call this our EY. Call that RAY and RAX. So we can do our sum of forces. We'll take the geometry off of the top drawing. So we'll take our sum of forces in the x direction. That's just RAX. And since there are no side loads imposed on this one, it's all 0. So no RAX. In the y direction, we get the same old with RAY plus REY, the up forces. And then we've got the down forces, 14 kips. So we've got down 14. So our moment equation is the big one here. We'll pick A as our pivot point. So we have our sum of moments about joint A. E is the full 24 feet away. So we have 24 REY. And that would be a counterclockwise moment. So it's positive. 18 feet away, 3 bays away, we've got that 4 kips. So we've got 4 times 18. And that should be, what, 72? I'm not trusting my mental math right now, but yeah, 72. So pinned at A, we pull down over here at D. That would be a clockwise, so minus. And then we've got the 10 kips at the midspan. 10 kips halfway across, that's 10 kips at 12. So that would be 120, also clockwise. So there we've got our moment equation. And that one we can solve. If we combine together the 72 and the 120, we've got 192. So we've got 24 REY equals 192. Divide both sides by 24. And REY equals 8. And that's 8 kips. All right, so 8 kips. So if our EY is 8 kips, we can go back to our y direction equation. What can we add to 8 kips in order to get to 14? Looks like 6. So our AY, 6 kips. So we can go back to our original drawing here and draw that in. So our AY was 6 kips. And our EY was 8 kips. And we expected Let's see here. We expected that that there'd be a roughly even split between these two. And so we'd expected a roughly even split. We got 10 kips up at the top. We have 5 kips. We'd expect 5 kips on each side. But that 4 kips throws it out of balance and requires that there be more force on the right side than the left. So that's why we see an imbalance here, 6 kips on the left and 8 kips on the right. So there's our external problem. So now on to the method of sections. Now the method of sections requires that we cut through the truss in a way that only exposes the forces in 3 of the unknown members. So if we cut through in a way that exposes 4 members, we'd have too many unknowns. Now in this problem, it's asking us to find 4 members. There's never a guarantee that you're going to be able to solve the problem in one setup. You might have to do multiple cuts, or you might have to do method of joints to get all the information you want. But it seems like with these 3 right here, kind of all in a line, it's sort of leading us toward drawing a section that's going to cut through right here. That'll at least get us these 3 members, member BC, member CH, and member GH. We'll figure out after we do that how we can get member AB. So our table is going to look something like this. We've got 4 members that we're looking for, member BC, or member AB, member BC, member CH, and member GH. The loads are all in kips, and we want tension or compression. So to work with a section of the truss, we have to close that system boundary either to the left or the right. And it looks like the way this is drawn, the left would be the better choice. If we close to the right, we can certainly make it work, but it's got a lot of other forces we'd have to deal with. This 4, this 10. So there's a lot more extent to it, a lot more math. Probably easier to close like that. That way we just catch this little section right here. So let's see how that section looks, and then we'll draw up our equations of equilibrium. All right, so start out with drawing the parts that are entirely enclosed in the system boundary. That's A, H, and B. So we've got A to H, A to B, and B to H. So that's H, A, and B. And then we know we've got a 6 kip force pushing up there. Now we can draw what we've cut through. We've cut through member BC. So we've got a part of member BC there, and then we've got where we cut it. And then we've got this force that we've exposed. And remember that in method of sections, we always draw the forces as pulling forces. That means we're assuming tension. We're assuming that the part that we cut away was pulling on the part that we're keeping. And that assumes tension. That way, if we get a positive answer, we know the member's in tension. If we get a negative answer, we know it's in compression. So that'd be the force due to member BC. Then we've got a piece of member GH, and then where we cut it, and the force that member GH carries. So FGH. And then we've got this piece here, right where we cut it, and then a force. That'll be the force due to member CH. So if we can solve this, we'll be able to get our three unknowns. We'll figure out the loads and the state of tension or compression of BC, CH, and GH. We're going to need an angle or two here to make this work. Fortunately, with a truss, with especially a roof truss, the angles tend to be kind of repetitive. If you can figure out one of the angles, you can usually figure out all the rest of them. So for example here, we're likely to need an angle in here. And the best thing to do in this kind of situation is to not try to find the total angle, because that's not really going to help you. Remember, we need angles to vertical or angles to horizontal. So what you can do is draw a little horizontal reference here and figure out what the angle is there. Because of essentially symmetry, and we can argue it and we can actually calculate it out and prove it, this angle is going to actually be the same. So the angle that CH is below the horizon is the same as the angle GH is above the horizon. And there are a couple ways to see that, but if I draw that horizontal reference here, you can see that this angle and this angle are going to end up being the same, because these two triangles, ABH and BC or CBH, they have the same measurements. It's the same height here because they share it, and it's the same base. So if you use the Pythagorean theorem, these have got to be the same lengths on the hypotenuse, and so the angles all have to be the same because the physical sizes are the same. Think about it this way: the tangent's got to be the same. It's opposite over adjacent, opposite over adjacent. Well, this triangle here is exactly the same. In fact, since this is just a slope to horizontal, that angle and this one have to be the same. And here we have two parallel lines cut by a line. And we saw this before, that the corners of this little Z shape, that little zigzag, are the same. So if we find this angle, we know this angle, and that angle. So there's only one angle involved in this problem. And fortunately, finding this corner angle at A is pretty easy because we know we've got 12 feet along the base and 8 feet up. So we got 8 feet and 12 feet. We can do inverse tangent of 8 over 12 and find the angle's 33.690 degrees. So 33.690 degrees. So that'll be this angle. And it'll be this angle. You might have to stare at that for a little while and make sure that the angles make sense, but they do. It'll only be that one. So let's go ahead and set up our equations, see what we've got. If we take our sum of forces in the x direction, so we'll take our sum of forces in the x direction. We've got all of FBC. We're going to have a piece of FCH, and it's going to be the adjacent piece, so cosine. It's to the right, though, so it's positive. So we have FCH cosine of 33.690 degrees. And we're going to have a piece of FGH, so it'll be FGH cosine, again, adjacent side, cosine of 33.690 degrees. That's everything in the x direction. Got nothing else in the x direction. In the y direction, we've got a positive 6 kips. We've got nothing from FBC. We're going to have a force downward from FCH, and that'll be the sine. So minus FCH sine of 33.690. FGH pulls up, so that'll be plus FGH, also sine of 33.690 degrees. So that'll be equal to 0. Nothing's looking good so far as being able to solve. The x direction's pretty bad. We've got 3 unknowns in that. We've got 2 unknowns in our y direction equation, so we can't solve that one just yet. Moment equation is going to have to save us here. Now, the moment equation all depends on what pivot point we pick. And we only really have 3 candidate points here. It's going to be the 3 physical joints in the problem, A, B, and H. Now, if you go and pick A, you're going to knock out FBC. You're going to knock out FGH, but you'll have a moment due to FCH. And that's at a weird angle, and finding the perpendicular component of that could be strange, and it looks like a big mess. B, similar problem. You knock out FBC, but then you've got weird angles here to try to figure out moments from. So the only point left is H. And H would be where I'd jump to because it knocks out the 2 forces that are at weird angles. Everything else is pretty easy to calculate a moment from. So it looks like joint H is where to go there. So I'll take my moments about joint H. If I pick pivot point H, FBC will have a moment, and the 6 kips will have a moment. Well, that 6 kips line of action is 1 bay away, and each of our bays are 6 feet here. So we've got 6 times 6, 36 kip feet. Pinned at H, pushing up at G, that would be a clockwise rotation, and clockwise rotations are negative. So we got negative 36 there. The member FBC is right there, or the force due to FBC is right there. So this distance right here is our arm, and that distance isn't given to us in the problem. However, we can pretty easily figure that out. You have to do a little bit of geometry here, but it's not too bad. One way to argue it is to look at scale. If you look at this big triangle right here, it's 12 feet wide versus 8 feet tall. If we look at the little triangle right here, it's basically the same shape of triangle. It shares the same angle. Technically, to use the mathematical term, triangle ACG is similar to triangle ABH. And when 2 triangles are similar, they share angles. And because of that, they share proportion in size. They're not guaranteed to be the same physical size, but they have a proportion to them. So if the base here is half of the bigger base, the height is going to be half of the bigger height. So this distance is half of the full distance, so it's going to be 4 feet. You could also, using your angle here, now that you've got that, you could do a little bit of trig and find that out. And there might be some round off error involved with that, but you get close to 4 feet. There, you could do inverse tangent of, tangent of x over 6, tangent of 33.690, and you'd get the right answer. But this is 4 feet. So this height is 4 feet there. So we've got an arm of 4 feet for FBC. So it's 4 FBC. And if we pin at H and pull to the right, it'd be counterclockwise moment. Counterclockwise moments are positive. So at least the moment equation looks like it can be solved in a reasonable way. So we can go ahead and solve that. And if we work out the algebra on it, it's not too bad. And we get that FBC is a positive 9 kips. We add 36 to both sides, divide by 4, we get 9 kips. So member BC carries 9 kips, and because it came out positive, we know it's in tension. So we can go to our table here and fill in for member BC 9 kips in tension. Now, a little bit of a difference in this problem from some of the others we've done. Normally, we can just go and substitute in and solve the equation, but the only place where we can substitute in this 9 kips is up here in our x direction equation, and we can do that. We can replace FBC with 9 kips, but we still have 2 unknowns in both equations. We've got some simultaneous equations to deal with here. And sometimes that happens just by the geometry. There's no way to get around having simultaneous equations. So a little bit of review on doing simultaneous equations here. Let me move the 9 over to the other side, so it'll be negative 9. And we'll write our x equation down here. We have FCH cosine of 33.690 degrees plus FGH also cosine of 33.690 degrees. That's going to be equal to negative 9. So that's our x direction equation. And then our y direction equation from the top right there, if I subtract 6 from both sides to put the 6 over here as a negative 6, I'll end up with negative FCH sine of 33.690 degrees plus FGH sine of 33.690 degrees. So if we remember back to solving simultaneous equations, the way we solve simultaneous equations is by finding a built-in sign difference if we can, making the coefficients have the same size, and then adding the equations together. And this one's not too bad compared to others. Here we've got our built-in sign difference on FCH. It's positive in one, it's negative in the other, so that's our candidate for elimination. We just have to make the coefficients the same, and the easiest way to make a coefficient the same is to just divide out the coefficient you've got. So in the top equation, we'll divide through by the cosine of 33.690. And it just so happens that we have exactly the same term here, cosine 33.690. So the only thing that's going to be ugly is this negative 9 divided by cosine of 33.690. So if I go through and I divide each term by the cosine of 33.690, I'll get just plain old FCH here. I'll get just plain FGH there. And then I'll get negative 9 divided by the cosine of 33.690. And that's 10.817. So I get negative 10.817. We do the same thing on the x direction or the y direction equation. We're just going to divide by the sine of 33.690. That'll make FCH, negative FCH sine, it'll make it into negative FCH. It'll make FGH just FGH. Signs will cancel out. And then the ugliness we have would be negative 6 divided by the sine of 33.690. And that just so happens to come out to be negative 10.817. So kind of an interesting way that's set up there. But sometimes that happens. We get some symmetry in the problem and we're seeing the reflection of that. So let's just verify everything was good here. 33.690 sine. And double check that. I'm always a little suspicious of coincidences when I see these come up. So we'll just make sure. Yep. We got some proportionality going on in this. So that's why that came out that way. So now those two equations, we can add those together. We add FCH and negative FCH. Those cancel out. We get 2 FGH equals negative 10.817 times 2. That's negative 21.634. Divide it by 2. And FGH is a negative 10.817. And that's Kipps. So came out negative. So that means we know our direction is wrong. We assumed, so for FGH, we assumed tension. It's actually compression. Again, the top of the structure, typical, that's going to be in compression under horizontal loading, under vertical loading. So FGH 10.817 in compression. Now that we know that, we can go back to one of our original equations and figure out what what FCH has to be. So let's go back to the y direction equation for that, just in case there's some error in here. I always like to go back further. So we'll go back to those. FGH was negative 10.817. So we've got 6 minus FCH sine of 33.690. The minus will show up there. It's 10.817 negative times the sine of 33.690. And that gives us a negative 6. So that's an interesting way that this is loaded. So that equals 0. Notice what happens here with our 6's. We have 6 plus negative 6. That's 0. So the 6 and the negative 6 cancel each other out, and we end up with negative FCH sine of 33.690 equals 0. The only way FCH times the sine of something could be 0 is FCH is 0. So FCH is 0. It's unloaded. So under this particular loading, member CH doesn't carry any force. So member CH, we can't say whether it's in tension or compression because it's not carrying anything. So there we go. Some simultaneous equations, so some good review there. Sometimes they come up and you just have to deal with them. Can't always pick a coordinate system that will get us around it. And member FCH carried no load. Now we aren't quite done with the problem. We still want member AB. And the easiest way to get member AB is to do method of joints at joint B. Once you've developed some skill doing method of sections and method of joints, you can combine the two together. Unless the problem says exclusively use method of sections to solve the problem, method of joints is valid. Just keep straight tension versus compression and how that looks in method of joints versus method of sections. So what I would do here, rather than trying to do some other cut, because you really don't end up with much to cut through here, you could, I suppose, loop all the way around on this side and figure it out that way, but that's a lot of extra work. If we draw our free body diagram for joint B, it's going to look something like this. We've got member BC. Well, we know something about member BC. It carries 9 kips in tension. And from the point of view of method of joints, tension shows the joint being pulled toward the member. So member BC, if that's in tension, it's trying to pull joints B and C closer together. So joint B is pulled to the right with 9 kips. That gives us a pretty good guess as to the direction of member AB. And then we've got BH, which is a toss-up, so we could draw it up or down. I'm going to draw it down. Well, that's our free body diagram. Now, 2 things to notice. One, we only want one of these. We only want FAB. We don't care what FBH is. And so we don't really need a y direction equation here. The x direction equation will do it for us. Second thing to notice is the way this is drawn, this can't be 1 as a tug of war. If FBH is anything, it's going to throw everything off. It's going to be dynamic. It's going to move. While FBH, the only way this could look like equilibrium is if FBH is 0. Since FBH is the only y direction force, then it must be 0 to be in equilibrium. So member BH is also unloaded in this particular truss. So all we're really left with is our x direction here. So we can do our sum of forces in the x direction and work through it formally, or you could just realize you've got two forces pulling in opposite directions. The only way we can have equilibrium is if they're equal. So member AB carries 9 kips of force. And since member AB is over here, it's pulling on joint B. So member AB is also in tension. So not too hard to finish that one up just by doing a little method of joints. So members AB and BC both in tension, and member GH in compression, member CH unloaded. So roof trusses can get a little complex. They can be a bit of a challenge to work out. You almost always end up, depending on how you make your cuts, you almost always end up with simultaneous equations to solve. So got to be able to deal with that. Any questions on that one?
Nope.
All right. Well, let's take a break, and I'll be back in a few minutes, and we'll put another problem up for practice. All right. So here's our practicum problem for tonight. The solutions, or the answers at least, are in red. So if you go and copy off the problem in black, you can work it out and check your answers quickly. If you get the right answers, then I don't really have to stay tuned for the solutions. But now that we've finished it in class, we'll go ahead and go over it. So first thing we have to do in this truss, first, always a good idea to get a look at it, make sure you get a good feel for where things are and how it's being loaded. Here it's all loaded at this right end. There's a pretty heavy download or downward loading on point F, and then we've got some pulling forces here at F and E. The support, the roller support, instead of being all the way in the end at the end of the truss, is in the middle. So this is what we call a cantilevered structure. Part of it is hanging over its supports rather than being supported just at the ends, simply supported. So that pin support is probably going to have to do quite a bit. It's got to oppose that sideways pull, but then we've got such a heavy force pushing down here, it's very likely that this end is going to want to come up unless the pin support pulls down to oppose it. So we've got some sort of lever action going on because the pivot point, or the roller, is at C. It's at C instead of at E. So let's go ahead and work out the external problem. So we'll go ahead and sketch the problem out. Remember, for the external problem, we don't need anything other than really an outline of the truss and where its supports are. So we've got RAX and RAY. We've got in the middle RCY. And then we've got all this loading at the end. There's 5 kips here, 5 kips there, and 15 kips. And we'll get the geometry off of the full scale drawing. So we can do our sum of forces here in the x direction. So until we need the geometry, we'll push that off. So sum of forces in the x direction, we have RAX positive. We've also got a positive 5 and a positive 5. So that equals 0. So RAX is a negative 10 kips. The negative there means we assumed the wrong direction. So the 10 really has to pull to the left rather than push to the right. Sum of forces in the y direction, we've got RAY plus RCY minus 15 equals 0. So that's the same thing all the y direction equations typically say. The forces pushing up have to be opposed by the forces pushing down. And then we need our moment equation. And the most natural point to pick here would be A. Well, the roller at C is halfway across the truss, and this truss was 24 feet wide, so it's 12 RCY. If we're pinning at A and pushing up at C, we'd have a counterclockwise moment, and counterclockwise moments are positive. So 12 RCY. If we're picking A as our pivot point, anything with a line of action that goes through A will not have a moment. So this lower 5 kip force doesn't have a moment. So we can ignore it. The upper 5 kip force, on the other hand, that has a line of action that is, according to our drawing, 4 feet away from the pivot point. So the arm for the 5 kip force, the upper 5 kip force, is 4 feet. 4 times 5 is 20. If we're pinned at A and pulling to the right over here at the top, that's going to cause a fairly weak but clockwise moment. Clockwise moments are negative. And then we've got this 15 kip force. According to the drawing, each bay is 6 feet. So we are 6, 12, 18 feet away. The line of action for that 15 kip force is 18 feet away. So we have 18 times 15, and 18 times 15, we've got 270. Now that is also going to give us a negative moment, since if we're pinned here and pushing down, that would be a clockwise moment. So there we have our equations for the external problem. Well, if we solve through these, we'll get that 12 RCY has to equal 290. So RCY has got to equal 290 divided by 12, which is 24.167 kips. Came out positive, so RCY is really up. When we go and take that into our y direction equation, though, we got 24.167. When we take 24.167 and subtract off 15, we get a positive 9.167. So we have RAY plus 9.167 equals 0, which means RAY is negative 9.167 kips. So our direction's wrong for RAY. It's got to be pulling down. So this fairly heavy load here is trying to lift up the other end of the truss. And so to keep it in equilibrium, the support has to pull down on it. So that's our external problem, and those are the answers we have right there. RAX was 10 kips to the left, RAY was 9.1670 down, and RCY was 24.167 up. But now we get to the real meat of the problem, and that's doing the method of sections. Now, first we check which members we need. We need GH, CG, and CD. Well, GH is right here. CG is right there. And CD is right there. So those are the 3 members that we want to get. And fortunately, we've got 2 fortunate things in this problem. One, we can cut through that all at once, because if we draw a cutting plane right through here, that will cut through all 3 members we want, and only the 3 members we want. The second thing that's a benefit in this problem is that all the members are either horizontal or vertical. So no sines or cosines on any of our unknowns here. So that's a benefit too. If we wanted CH or G or DG, then we'd have an issue. But with the members they've asked for, we don't need to have any sines or cosines. The problem really comes down to which direction you choose to close in. Remember, you can always close to one side or the other. And the problem could be significantly easier or harder, depending on which direction you can close in. In this case, we're right in the middle. If we close to the left, we don't have any external forces to deal with except for our reaction forces. we'd have the 10 kips and the 9.167 kips there and the 24.167 kips there. But something strange happens in this one. We haven't seen a problem yet that does this, where we can cut through and actually close around something that doesn't touch any of our supports. Essentially, we can close through a floating section of the truss. And if we close to the right, we'd interact with these 15, 5, and 5 kip forces, but we wouldn't actually interact with our supports. And if you were really familiar with doing method of sections and you knew that you could do that, you might realize that you don't even really need your reaction forces to solve in this problem. This happens whenever you can close around a floating section of the truss, a part of the truss that isn't touching one of the supports. You actually don't need to find the support forces. So that happens from time to time, but it's rare. But in this case, we could close around to the right. And I'm going to go that way because that's a better way of doing it. It doesn't involve anything that I calculated down here. So if I made a mistake down here, my reaction forces wouldn't throw off my answer. So I'm going to close to the right here just to show how that can be done. It's really no different than closing to the left. It's just we have different forces to interact with. So let's go ahead and draw the part of the truss that is entirely enclosed in the bubble here, and that's this these two kind of back-to-back triangles, this sort of trapezoid setup that we've got here. Something that kind of looks like that with something like that. We've got a 5 kip force here. We've got 5 kips here. Got 15 kips here. Then we've got what we've cut through. We have a piece of member GH, and then where we cut it, and the force due to member GH. And remember that we draw our forces, our unknown forces, so that it's putting the member into tension. That means drawing to the left here in this problem. Down here, we've got a piece of member CG, and then where we've cut it, and the force due to member CG. And then we've got over here the piece of CD and the force due to member CD. So because we don't have any sines or cosines that we need to do, everything's at 90-degree angles. We're horizontal and vertical. We don't need any angles or anything like that. So there's our section. So let's do our sum of forces in the x direction. Well, in the x direction, I've got a negative FGH. So we've got negative FGH, we've got a positive 5, and we've got another positive 5, and we've got a negative FCD. So that's our x direction equation, which if we clean it up a little bit, we have negative FGH minus FCD minus 10 equals 0. So that's our x direction equation. In the y direction, we have negative FCG and a negative 15. No other y direction forces. So that's pretty clean there. Then we need to pick a pivot point, and generally picking the pivot point at the intersection of the lines of action of the most unknowns will give you the best benefit. And in this problem, that's going to be joint G. So we'll take our moments about joint G because that's going to knock out FCG. It's going to knock out FGH. It's also going to knock out this 5 kip force since the line of action of that 5 kip force goes through G. So if we take our sum of moments about G, we've got this 15 kip force 1 bay away, so that's 6 times 15. So we've got 6 times 15, we've got 90 there. If we're pinned at G and pushed down we get a clockwise moment, and clockwise moments are negative. The 5 kip force here doesn't contribute anything. This lower 5 kip force does, and that 5 kip force is 20 feet away. So the 20, or the not 20 feet, is 4 feet away. So we've got 4 feet times 5, that's 20. Pinned at G, pulling to the right, that's going to be a counterclockwise moment. So counterclockwise moments are positive. So we've got positive 20, negative 90. Then we've got FCD. FCD has the same arm as this 5 kip force down here. It's 4 feet away from G. So we have 4 FCD. And if we're pinned at G and pulling to the left, that would be a clockwise moment. And clockwise moments are negative. So we have negative 90. We've got a positive 20 and a negative 4 FCD, and that's equal to 0. So all in all, not terrible equations of equilibrium to solve. I don't see any sines or cosines, so that makes things at least a little nicer. If we simplify some things down here, we got to be careful with signs because we're likely to see negatives showing up in our answers since we know all of these members are likely not going to be all in tension. So let's start with the moment equation here. If we combine the negative 90 and the 20, we get a negative 70 minus 4 FCD equals 0. If we add 70 to both sides, we get negative 4 FCD equals a positive 70. Divide both sides by negative 4, and FCD comes out to be negative 17.5, and that's kips. Now, because it came out negative, that means our assumption was wrong. Well, we assumed that the part of the truss we cut away pulled on member CD, what was left of it, putting that member into tension. But we now find that that assumption was wrong. So the opposite of tension is compression. So member CD carries a load of 17.5 kips in compression. And that's what's stated up here in our answer. That member CD carries 17.5 kips with the parentheses C, that means compression. But we got to be careful. Anywhere else in the equations where we see FCD, we've got to use that negative value. So that means when we go up to the X equation, we got to be really careful. Let's go to the Y equation first here. Let's add 15 to both sides, and we'll get negative FCG equals a positive 15. Well, if negative FCG is a positive 15, then FCG must be a negative 15 kips. So member CG, we had also assumed was in tension, but we got a negative answer. So member CG must also be in compression. And so if we go back to the page here, we've got member CG carrying 15 kips in compression. The only one left to get is GH, and we'll get that from the X direction equation. So I'm going to be really careful here in writing this up. Negative FGH minus whatever the value of FCD is. So if we write that down really carefully, we've got minus FCD. Well, FCD is this whole thing down here, negative 17.5. So it's negative 17.5 minus 10 equals 0. Well, use your arithmetic rules to kind of work that out.
Is that supposed to be plus 10 or no?
Yes, it is. Thank you. You're absolutely right. I think I was solving it in my head and I was trying to move it over. So you're absolutely right. That's a positive 10. Thank you very much. So we had 2 plus 5s there, plus 5s plus 10. Everything else should be good though. So now we've got negative FGH plus 27.5 equals 0. So negative of something plus 27.5 equals 0, that something's got to be a positive 27.5. And you could see that if you add FGH to both sides. So FGH comes out positive 27.5, and positive results mean tension. So 27.5 kips of tension. So we've done the math, got the math going. What we need to do is also supplement that with some understanding of the structure. So let's take a look at the structure and see how we can understand that these are in compression and in tension. Well, if you think about what's going on, basically you've got a big diving board kind of thing here where someone's putting a lot of load right here on the end of the board. Well, that's trying to take this whole section that's to the right of C and bend it down. Well, if it's bending it down, the bottom here is being squeezed together. Remember, if we bend something downward, the top would go into tension and the bottom would go into compression. So member CD is being squeezed on. We're also seeing member GD or member DG is going to be pulled apart. So that's going to be kind of a tension force as we're pulling this down. D is coming down, but G really can't go anywhere. So this is going to go into tension. Well, that's what's pulling down on the top of CG, putting CG into compression. And then member GH, well, that's feeling that force too. It's feeling the stretch of trying to bend this whole right side of the beam down, or the truss down. So member GH is in tension. So we can kind of go through and reason out that these are reasonable states of tension and compression. That's always something good to do, because in case you get flipped up in your math or you misinterpret tension or compression, or you miss a minus sign somewhere, you might catch it and say, well, I said for my math that CD was in tension, but physically it looks like it's getting squished together. So it's got to be in compression. Better check the math and make sure that it's adequately representing the system, that you haven't made a mistake. So that's that practicum problem. Now, if you're looking for more problems to practice and then see solved out, check last year's material. It was about this time that I started recording things last year, since we were all shut down, and such. You can likely find some examples of method of sections, likely a lot of examples, because in transitioning to online, we ended up taking a long time to do that. So we spent a lot of time doing practice on those. So if you look at the YouTube channel and look for stuff from 2020, you'll see some presentations with some more method of sections practice. There might even be some more method of joints practice there. So that's another resource for extra practice problems. You only get better at these by doing practice and working them out. So I strongly suggest doing that. Any questions so far?
Nope.
All right. Well, that's just about it for tonight. On Monday, we will take a look at frames, which in a couple ways are a little simpler, and a couple ways are a little more complex, but they generally don't involve a lot of sines and cosines. So not a lot of trig involved with them, but they are structures that we'll be working with, and we are again kind of rapidly heading toward our next exam. Likely looking at somewhere in the neighborhood of a couple weeks before our next exam. So we'll have another homework assignment out for that on frames, but we're getting close. All right. Well, if there's nothing else, have a good evening and have a good weekend, and I'll see you Monday evening.
All right, you too. Take it easy.
Thank you.